Professor Marco to have his seat. We start. Now we start this afternoon session, and I introduce Gabriel Rondon from Unesp de Rio Preto, and he's going to talk about lower bounds for the number of limit cycles in piecewise polynomial holomorphic systems.
Thank you. First of all, I would like to thank the organizer for giving me the opportunity to present my work today. I will talk about piecewise polynomial holomorphic system. I hope you find this topic interesting. The idea here is to use the complex variables tool to simplify and solve some problems in a subfamily of piecewise smooth system. So this is a piecewise smooth system, and we're interested to study a subfamily of piecewise holomorphic system. I divide the presentation into 4 parts. First, we introduce some preliminaries, some basic concepts and results, and after that, we establish our main result. Okay. First, we introduce the concept of holomorphic function. F is a complete value function defined in the domain V of C, and satisfies that the real and imaginary part are continuous. There is the partial derivatives, and the partial derivatives satisfy the Cauchy-Riemann equation. The holomorphic system have interesting properties. The equilibrium points are isolated. This type of system don't have limit cycles. The center focus problem is totally solved, and there is the field integral defined in a subset of a total measure in R2. Now we introduce the normal form for this type of system. This work was done by Garijo, Gazul, and Yarke. Okay. So, for example, if we have if W0 is a zero of f of order n, in this case we need to study the residue. So if the residue is not equal 0, we have this normal form, that is f and g are conformally conjugated. That is, conformally conjugated is stronger than topological conjugated. The difference is that the angle is preserved. Okay. In the case when we have a 0 of order n, but the residue is 0, in this case, f and this g are conformally conjugated. In this case, we have a pole. If W0 is a pole of f or order n, we have that f and this g are conformally conjugated. Here, I present some facet portrait of this normal form. For example, it is the squared case, it is the cubic case, and this is the quadratic case. Okay, and this one is the facet portrait of this case, and so on. Now we introduce the piecewise smooth, piecewise holomorphic system. In this case, we f plus f minus are holomorphic function. Okay. And the trajectory on sigma are defined following the Filipov convention. Okay, so if we consider, for example, the X as a discontinuity, for example, a tangential point is something like that, something like this. Okay, for example, if this part is a sliding region, we have this neighborhood of the trajectory. The trajectory search here, and after that they follow the sliding vector field, and after that they continue in this case. Okay, so it is a example of trajectory. And in this case, we have a second region. Okay. So in this case, the trajectories are concatenated, something like that. Okay, so it is the general idea. Now I introduced the Lyapunov quantities. We know this theory. That theory was done by Andronov. So the idea here is to have the coefficient in this context. Here, that's in the piecewise holomorphic system is more simple. Okay, it's more easy to compute this coefficient. Okay, so consider the system this one. Okay, fk is equal to this expression. Okay, assuming that the origin is a focus type, and the imaginary part of A is positive, where the first function is given by this expression. In the r theta polar coordinate, we can write this expression of the form. Okay, and if let R be the solution of 3 Xochitachi, we have this initial condition. Consider this equation. The idea here is to compute this coefficient. Okay, so we know that in smooth cases, the Lyapunov quantities are given for the fish k Xochitachi. This is not equal 0. It is known that this k is odd in the smooth case, but in the piecewise case is a little different. Okay. For more detail, you can see this paper. And now it is our first tool, first theorem. We consider the system 1, where f plus minus are defined in 2. Suppose that we have this function, then its first Lyapunov quantities are given by this expression. Okay, the idea is to make some application of this result. Now, consider the following definition. We say that P is a wave focus or order K of system 1 if the displacement function defined as this satisfies this expression where we have the field K minus 1 are the quantities are 0 and this quantity is not equal 0. Okay, so let me see. Here, for example, this displacement function, we have something like that. It is, and then continuity set aquí. If this is an initial condition, we reset here using f minus, so call this map f minus, and after that we take this initial condition, we reset here in a point, this point is a plot of f minus, if this is r minus r. So the displacement function here is, we studied this different, this one. Okay. Now consider the piecewise holomorphic system. This in this case S is a parameter. Okay. So to find Dynamic cycle here, we use the following proposition. If piecewise holomorphic system 1 has a wave focus or of order k at the origin, that the system 4 has at most k minus 1 Dynamic cycle quantity the multiplicity. However, if we have this condition, then there is real parameters small enough such that the piecewise perturbated holomorphic system 4 has exactly k minus 1 hyperbolic Dynamic cycle bifurcated from the origin. This condition is not necessary. We can have piecewise smooth system in general, and that result is that result hold. Okay. Now let's start with the applications. Let L n plus n minus be the maximum number of limit cycle. Okay, let this be the number of hyperbolic limit cycle bifurcated from the origin of system 1. So we have these tables. Okay, so for example, in the linear case, we got one limit cycle bifurcated from the origin. In the quadratic case, we got 4 limit cycles. Okay. To illustrate the construction of to get this theorem, we consider this proposition, the quadratic case. Okay, in this case, we consider the origin as an equilibrium point. Okay, so in that case, there is real parameters small enough such that 3 limit cycles bifurcating from the origin. So here we use the previous theorem and we compute the Lyapunov quantities. Okay, and here the idea first is to find the order of the focus. Okay, so we need to set, for example, V1 equals 0. We have some condition in the parameter of the system. Using that information, we set V2 equals 0, and we have some condition here. When in this case, we repeat the analysis. Okay, we set this V3 equals 0, and when we started this coefficient, we got this parameter. This parameter, in this parameter, we have a square root. So when we compute the for Lyapunov quantity, this expression is very difficult to determine if that Lyapunov quantity is or not equal to 0. For that reason, to remove that square root, we use rational parameterization. So in that case, we got this quantity. That is a rational parameter, but now we have a new parameter tau. So for that reason, when we compute these parameters, these Lyapunov quantities, the Lyapunov quantities depending of this parameter tau. Okay. After that, we compute the determinant of this expression, and we got this expression, which is not equal 0. Okay. So from previous proposition, we can conclude that there is a real parameter S1, S2, S3 small enough, so that the system 5 has 3 limit cycles. However, here we have 4 limit cycles. Okay? To get that number, we need to consider this perturbation. If we consider, in general, a piecewise perturbed holomorphic system, it is a perturbed term. Okay? So in that case, if this coefficient is not equal to 0, then there is d different to 0, sufficiently small, such that 1 limit cycle bifurcates from the origin. So in the quadratic case, we have 3 limit cycles plus 1, 4 limit cycles. Okay. Now, here we have, in the linear case, we get, in this case, using the Lyapunov quantities, 1 limit cycle. However, in the literature, when we study the piecewise smooth system, we know that there exists 3 limit cycles. Okay? So there are some examples, and we know the uniform bound of in the linear case is, in this case, is 8. That work was done by Douglas and Fernando and Victoriano. So what happened here in the holomorphic case? For that reason, we employ here the Mobius transformation to answer that question. Okay, it's one way to do that. So in this case, we are proving that there are piecewise linear holomorphic system with at least 3 limit cycles. Okay, so we consider a linear case. Okay, and after that, it is the key in this analysis. We consider this Mobius transformation. okay? And we get this piecewise holomorphic system, okay? It is the same quadratic case, okay? We know that in this case, when the origin is an equilibrium point, we have 3 Lamet cycles, okay? So these 3 Lamet cycles are transformed via this conformal map into 3 Lamet cycle of the origin system near infinity, okay? Now, consider this piecewise holomorphic system where the unit circle is the discontinuity. The idea is to shift the analysis here and to make the study here, okay? So for that, we introduce this definition. In general, the Mobius transformation is given by this expression where we have this condition, okay? This transformation map the extended complex plane, including infinity, onto itself. Recall that phi is a different body, okay? So we got this result here. Given the piecewise holomorphic system 9 and the Mobius transformation 10, the push forward of the differential system this under the Mobius transformation is given by this expression, okay? So in this case, very interesting because instead to make the analysis here, we shift the analysis and study the system here, okay? And after that, we can return, okay? Because phi and his inverse are Mobius transformation. For example, consider this Mobius transformation, which map the unit circle onto the x-axis, okay? In that case, we have this system. For this system, the x-axis is the discontinuity, and G plus minus is the push forward of F plus minus. Here we need to make a remark because phi is defined in the extended complex plane. So there is a point here, first A, such that it is infinity. So in that case, if we have a periodic orbit here passing through that point, when we apply phi, the imagine of phi is something like that. That is, the curve don't close in the infinity plane. It closes in the infinity. Okay. So in that case, we need to identify this Lamet cycle. When we study here, we need to make another analysis. Okay. Another property interesting in this case, for example, if F is a normal form given in this proposition, then the transformed system, this will exhibit the same normal form with respect to phi and 0. That is, if we have C squared, we apply phi and we get the same normal form. Okay? Here we have another properties. For example, if we have here a periodic orbit, we apply phi, and the imagine is a periodic orbit. These preserve the same orientation, and they are the same. They have the same period. Okay. Now consider this system. I would like to do the same analysis, but in this case, the discontinuity is the unit circle. Okay. So in that case, if we consider this system, there exists a sufficiently small real parameter S, such that there exists one Lamet cycle bifurcated from the origin. Okay? So what is the idea here? again, we use the theorem asterisk, okay? We get the following quadratic piecewise holomorphic system, this one, and we can compute the Lyapunov coefficient, okay? Because we can apply the first theorem, okay? So in that case, we have this, and this is not equal 0. And the determinant of the expression is p, which is not equal 0. So for proposition asterisk, we can conclude that there is a real parameter s small enough such that system 15 has one limit cycle. Since we have this expression, then system 14 has one limit cycle bifurcated from the point I. Okay. Okay, it is the last part. It is about simultaneous bifurcation of limit cycle for piecewise complex system. In this case, we consider a center. Okay, we consider this differential equation has a center at P, and we consider this parameter, this perturbation. In this case, epsilon is small enough. Okay, so in the r theta coordinate. 16 is converted into this this equation here, where f plus minus is given by this expression. Okay. So in that case, we know that if sin plus 0 of this Minkov function provided for epsilon small enough, hyperbolic limit cycle of the piecewise smooth system 17. That tends to r equals r0 when epsilon tends to 0. Okay. Really here, the Minkov function is the difference of m plus and n minus. Okay. In this case, the function this is the Minkov function in the piecewise smooth system. So, very interesting in finding an equivalent expression of AT when the unperturbed system is a holomorphic system. Okay? So, suppose that P is a center of a holomorphic equation. Okay? Then there exists a conformal map such that this differential equation can be written of this form. Okay? The map phi is called the linearizing chain of this differential equation at P. Okay? With this hypothesis, we get this result. Consider the piecewise complex system 16. Suppose that phi is a linearized chain of this differential equation at P, such that we have this condition, okay? And then each simple 0 of r equal r0 of this Minkov function, where m plus m minus is given by this expression, provided for epsilon small enough, hyperbolic limit cycle for the system that tends to r equal r0 when epsilon tends to 0. So consider this particular case. We consider this f, okay? In this case, the factor portrait of this vector field is given by this this factor portrait, okay? This figure. So in this case, we have two centers, in 1 and minus 1. So when it is the case when epsilon is 0, but when we consider the perturbation, it is the factor portrait in that case, okay? So in this case, the idea is to know the number of limit cycle, okay, bifurcating from minus 1, and the number of limit cycle bifurcating from 1. And after that, we study the simultaneous analysis, okay? In that case, that analysis is complicated. In general, the Minkov function is an analytic function. So in that case, we need to work a lot about that. So to do this analysis, we can do the following analysis. We consider this part, okay? We can make the analysis around minus 1, okay? The analysis in one is similar. We can we can translate this analysis in the another one. So it is enough to study here. We apply phi, okay, and we get this system here. So instead to make the analysis here, we shift this analysis and we study the system here, okay. Okay, this is a tool that we have used when the Milikov function is polynomial. When the Milikov function is analytic, the analysis is different. It's complicated, so we need to make another analysis. But here we present this case when we have the Milikov function has or is a polynomial function. So in that case, let f be a parameter family of polynomial. We know the discriminant of polynomial p given by this expression. This is the resultant of p and its derivative. Now consider this lemma. Let this polynomial function, okay, in omega lambda this set, okay. So assuming that there is a connected open set here, so that we have this condition. For some lambda 0, this function has exactly m zeros in omega lambda 0, and all of them are simple. For all lambda, we have this product is not equal 0, and the last one, for all lambda, this resultant is not equal 0. In that case, for all lambda, we know that this has also exactly m0, and all of them are simple, okay? It is the tool in that case. So, using that, we got this result. Again, it is the simultaneous case. So, for example, here, you can see, in this case, for example, when m is equal to, m is the degree of the one, okay? The perturbation function. So, if m, for example, is 2, we can at most get this configuration, phi 1 or 4 2, okay? So, in general, we can have 5 Lyman cycle bifurcated from 1 and 5 Lyman cycle bifurcated from -1. So, we can have the question is possible to get the configuration phi 5, phi 4, phi 3, phi 2. So far, we don't know that answer. So far, we only know that part because in that part we have a analytic function. The Milikov function depending of analytic function. So in that case, the analysis is very complicated. So, but in the polynomial case, in the first part here, we know that information. It's more easy because we can use this tool. Okay. And it is a holomorphic case. It's more simple. It's simpler. Okay. So in that case, for example, in the case when m is equal 1 or 2, we have this configuration. When we have this condition. Okay. So in that case, the configuration, for example, we can have 0 2, 1 1, or 2 0. Okay. And so on. Okay. It is the bibliography. We have some that we have used. Thank you for your attention.
Thank you, Gabriel. So we have time for one question or comment. So we thank Gabriel again. So our next speaker is Professor Cláudio Pessoa from Unesp de São José do Rio Preto, and he's going to talk about nilpotent centers on center manifolds as limit of Hopf centers.
Okay, thank you, the organizer, for the opportunity. I consider a vector field in R3 having a singular point P, such that the linear part of the vector field have the following Jordan canonical form, with lambda different from 0. After change of coordinates, linear change of coordinates, I can put this the system associated vector field in this form. Where these functions are analytical functions with the expansion with degree at least 2. By the center manifold theorem, there exists an invariant bidimensional série manifold tangent the XY plane for R. Sorry. Okay. This manifold is called center manifold. This is, in general, is neither analytic nor unique. The system restricted this manifold have this form. Becomes a planar system. In this case, I have the origin is a singular point, a nilpotent singular point. There is a theorem that classifies this singularity. Is the Andrea theorem. In particular case, there is conditions for the singular point is a monodromic singular point. Are these conditions? The classical Hopf center, the center problem for Hopf centers consists in determine when the origin is a focus or a center. This is the classical theorem for Poincaré-Lyapunov. The theorem affirms that the origin is a center if only if there is a first integral such that it begins with these terms. In this paper of Libre, Giacomini, Gile, Garcia, there is a result that use the classical Poincaré theorem for classify the origin, if it is a focus or center. This is the result of Libre, Giacomini, Garcia. In this result, state here, the problem, the center focus problem for nilpotent singularity of this form is equivalent to the center problem for Hopf points, but for this system here. I have this system with a nilpotent singular point at the origin. And I consider unfolding of this system and we have a center for these systems if only if I have a center for this. And here, these functions f1 and f2 satisfies these conditions. This is the result of the plan. I would like to extend this result for three-dimensional vector fields with a nilpotent singular point. Okay, but I have this system where the origin is a nilpotent singular point on the center manifold. I can use the same equivalent result of Poincaré-Lyapunov for determine when the singular point is a center or focus. If this is the result equivalent to the results from Libri, Garcia, and Giacomini for R3. We have this system, and the system has a center on the origin, a nilpotent center on the origin, if this system here also have a Hopf center of the origin, where the functions f1, f2, f3 satisfy these conditions here. Okay. In this case, I can use the Lyapunov center theorem for determine when the origin is a singular point. I consider a formal series with this form, and I do this inner product. And eu tenho this is a Lyapunov coefficients, and these coefficients give the center conditions for this system here. Okay, but in this sense, I say the center here, nilpotent center here, is a limit of Hopf center of the system here. This is the reference for the plan, the original result, and this is my result and the Lucas Queiroz for nilpotent centers on analytic center manifolds. Thank you for your attention.
Thank you, Claudio. Any questions or comments?
Can you explain how you use this last condition of perfume? This last slide here. How it works?
Why?
No, yeah, this F and H. Why?
Okay. This FH appear the proof of the theorem because I need to do change of coordinates because the idea is to restrict the system center manifold and there is a change of coordinates that the system associated is reversible. And in this change of variables, these functions appear. You have to implement, for implementing the algorithm, it's necessary, which here F1, F2, F3, generic.
So you suppose that the center manifold is analytic?
Yes,
Beside what?
it's necessary. It's necessary because the center, the nilpotent center is not equivalent as existence of the analytic first integral, like the Hopf center. The Hopf center is a center if there exists a first integral, analytic first integral, but in the nilpotent case it's not true.
Anyone else? No, so we thank Claudio again. So we have about 12 minutes for the next talk.
For this conference, Antonio. I thought I had knew him in the 2005, but no, we met before in Imperial College, you were telling me. But in any case, for me it has been great to know you, and in fact my most cited paper is a paper with you. And you're a lot of success, thanks to you. So, okay, this is going to be a talk in a different area, celestial mechanics. Some of you know very well the area, some others know. The talk has half of the part an historical approach to the problem. So if you also know this, sorry about that, it's going to be easy, but I thought that it's interesting to know why this problem is important, etc. No? So, it's a very old question, no? To know if, it's a very old question to know what happens if you put three bodies in the space, just assuming that they move to the mutual Newtonian attraction, gravitational attraction, and to understand what can be the final motions of this problem. So I am interested in knowing not what happens at any time, but what happens if you lose time, I mean, if you let time go into, let me say, to the future, to the past. No? And lots of mathematicians and astronomers trying to answer this question from very long time ago. Here I began by Copernicus, Kepler, but probably I miss lots of them, no? But lots of them trying to understand this problem. And in fact, there is a very important name for all of us, that is Poincaré. He was the one that introduced the tools of dynamical systems in this problem. So I'm going to explain a little more about that. And also say that, well, for this community is not necessary, but I say that the problem of n bodies in the space is a classical problem of dynamical system, because you have some bodies, some initial positions, some initial velocities, then the nature actor acts through the Newton gravitational attraction, and you want to understand what happens, and this is a deterministic system, so there is no possibility of randomness here. If you know the initial conditions and the initial velocities, theoretically you should know everything at any time, okay? So the first one that said something about the motion of the planets was Kepler, no? And what I read somewhere is that in fact Kepler was working with Tycho Brahe, the astronomer, and they didn't get on very well. And then Tycho was like hiding data to Kepler. I don't know if this is true. So until he died, Kepler couldn't access to all the data. And then he realized that with this data, he wrote history, he lost the famous Kepler laws, no? And the famous Kepler laws describe the motion of a planet around the sun. And everybody knows the laws, they are written here, no? The law of ellipses that says that the motion of a planet around the sun is an ellipse, and the sun is in one of the focus of the ellipse. The second is the law of equal areas, that if you make a line from the sun to the trajectory of the planet, if you put an interval of time, the area is always the same. So in this area here and this area here correspond to the same amount of time, and this means that in fact when you are closer to the sun, you move more than when you are far to the sun. So you are faster when you are close to the sun. This is the law of equal areas. And the law of harmonies that gives a relation between the period, because this is a periodic orbit, so it's a periodic motion, no? Even it's also a periodic orbit, with some period, and the major semi-axis. So this is a law that says that this square divided by a square is the same for all the planets, independent of which planet you take. Okay? So these were the Kepler laws that to me is amazing that he could make these laws just looking at numbers, okay? Because he was looking at data, and then he realized, he said that these laws worked. So no mathematics involved at this moment, some mathematics, but not a lot of them. So the question was then this one, no? Are Kepler laws true or not? And will the planets move all the time in these ellipses, or at least if not in these ellipses very close forever? Or something big can happen, like two planets collide, or one planet leaves the solar system, or whatever, no? So this is still an open question nowadays, so nobody knows this. And it's a fundamental problem of celestial mechanics, also called stability versus instability. You can imagine what is stability and what is instability, no? Was until the 16th century when Newton came in the game and gave his own other laws. So the laws of Newton that are in this philosophy Naturalis Principia Mathematica is the law of attraction, no? That says that two bodies attract each other with a force that is proportional to the masses and inversely proportional to the distance to the square. That is the famous G times F1 divided by R square, is a vector, the force is a vector, etc. And the second Newton law that says that when you have an object and you have several forces on the object moves, and the sum of the forces in the object has to be the mass of the object multiplied by its acceleration. Okay? These two laws together were the laws that allow to put mathematics in the problem we want to study, that is the n-body problem. The idea is here, so you have n bodies moving in the space, q1, q2, qn. Each body has three coordinates because we move in space, so these are 3n functions, okay? You have Newton's law that says that every body receives a force which is the sum of all the gravitational forces of all the other orbits made to it. The coordinates of the body are xj, ej, yj, cj. The velocity is the derivative, the second velocity is the acceleration. Things only depend on time. I am doing a very big simplification here that I am putting the bodies as points, okay? And you know that this is not true, of course. The point, the sun is not a point, etc. But this is only the first simplification, not the only one. And then you apply second Newton's law that tells you that if you take the body qj, the acceleration of qj times the mass of qj has to be equal to a force, and this force is the force that all the other bodies making qj. So this force is a function that will depend on all the masses and all the positions of the other bodies. And in fact, it has a very easy formula, okay? Because it's the sum of the forces, every force is a product of masses divided by the distance, etc. So this is a set of equations, a differential equation, so we are happy here because everybody understands ordinary differential equation. So when the mathematicians began to, and the astronomers began to solve these equations, what they were thinking is to try to solve them. Solve them means to find formulas for the solutions, okay? And these are then differential equations I said there depending on time. Can these equations be solved? This is the question. If we can solve these equations, we can answer if Kepler's law are true or not. Among other questions, we can answer this. And then another question is to think only in two bodies. So let's do the more simple case is that you only have two bodies. No? Two bodies is a stupidity, no, because if you think in the solar system, I will make a picture of the solar system, no? So this is the solar system, no, eh? This is the sun, that is very big, and then you have several planets, no? One, another, maybe three, okay? And then the masses of these bodies, compared with the mass of the sun, are very small, so it's not a stupidity to think, okay, to understand what this body does, let's consider only heat cells and the sun. To understand what this body does, heat cells and the sun, and we ignore the interaction between them. And then you have two-body problems all the time, okay? So it's a very nice, very normal thing to begin to understand the two-body problem, okay? And these are the equations of the two-body problem. You have two masses, M1 and M2, and this is the Newton equations, no? This is the force, that is the inverse to the distance, up to the square, but as it is a vector, you have to put the vector divided by the norm to the 3. This is the norm, the Euclidean norm. So you see here that you have 3 plus 3, because remember everybody has 3 coordinates. So 3 plus 3, 6 second order equations that become 12 first order equations. So you have a system of differential equations of dimension 12. And the equations are not very linear because you have in the denominator square roots of squares, etc., etc. So this is a horrible system, but it's a system that can be integrated by hand, which is curious because the trick is, I don't write it here, but the trick is to, instead of considering the bodies alone, you take the center of mass of the body, and then the center of mass of the body satisfies double dot equal to 0, so it's very easy to solve. Then once you know how the center of mass moves, then you consider the relative vector between them, and then there are some tricks, okay? That's so the two-body problem can be solved. You can find the orbits, etc. of the two-body problem. And then the solution is here. The possible motions of the two-body problem are here in this picture. Is the sun, that is, this is not moving because we are considering a relative motion. And then you have the planet can do 3 things. Can move in ellipses, that is what Kepler was seeing, okay? Can move in a motion that goes to infinity in the future and the past, but the velocity derivative goes to 0, that is called the parabolic motion, okay? And moreover, the picture is also a parabola. And then it can move to infinity, that is the blue, the dark blue, you see, that goes to infinity and the velocity goes to a constant. These are the possibilities. And this is what happens in the two-body problem. Of course, you cannot see the blue ones in the reality, you can only see the ellipses, no? Because are the motion that comes, no? This is the solution to the two-body problem. You have only these 3 possibilities, and always another thing is important: in the past and in the future you have the same motion. If you are parabolic in the past, you are parabolic in the future, etc. Okay, so question: what happens if we put 3 bodies, for instance, or 5 or whatever, no? Newton tried to integrate the 3-body problem because they were convinced that if you can integrate the 2-body problem, you can also integrate the 3-body problem. The trick is that you have a lot of first integrals in the system. This is the trick. And he was trying to compute the equations of the Earth, Moon, and Earth, Sun, and Moon system. He was not able. A lot of mathematicians at those times, the idea was that it should be a way to integrate the system, so they were trying and trying, etc. Laplace, using some previous work of Lagrange, he was convinced that he had proved that the n-body problem was integrable, and the reason was that he did exactly the trick. He was realizing that the model was using was ignoring the interaction between the planets. Okay? If you have 3 bodies, okay? 3 bodies, but you ignore the interaction between these 2, in fact you have 2 two-body problems instead of a 3-body problem. Okay? So you can integrate it, of course. Okay? And so the word is trying and we didn't succeed. of course. And then at some moment the question was a little different. Let's see if we cannot integrate everything, at least if we can say if the system is stable, if the solar system is stable. So even you cannot compute the motion exactly, can you say the question I said before, if the planets are going to stay more or less in these ellipses, more or less forever, or no, okay, or something dramatic can happen, you know? So the astronomers already had this stability question in mind, but after the Newton laws, this became a mathematical problem, okay? Because then we had equations to solve. And this basically what is here, no? And moreover, studying these equations in general was let me say, that was the origin of this new area that all of us are working on, that is dynamical systems. Okay? So the basic idea that is behind what I'm going to explain here is that to understand this problem here, that you have this three, put 3 or put 5 is not important. One body is bigger than the other, that's the main point. To study the motion between these 3 bodies as a perturbation, a system that is close to these 2 body problems we were talking before. Okay? So the interaction between these 2 are smaller compared with these 2 and these 2. So this term in the equations that appears somewhere will be smaller compared with the others. Okay? And this is what is called the planetary problem. And in the language of dynamical systems, we have a dynamical system, the equation of the n body problem, put 3 if you want, no? 3 body problems, close to another that are n minus 1 2 body problems. Okay? And then this one is integrable. And so we want to understand which are the effects that these small terms do to the previous one. Okay? And this is what we call as perturbation theory. It's what we do, people that does perturbation theory does this all the time. Okay? And the idea of studying this n-body problem as a perturbation of the n minus 1 body problems was an idea. And this is what we are very used to, no? So you have a system that depends on one parameter. The parameter can be 1 or 2 or 3, this is not very important. This epsilon can be epsilon 1, epsilon 2, epsilon 3. The system, when epsilon is 0, is integrable, so you know the solutions, you know what you like to study, and then you have another part that we call the perturbation, okay? And epsilon is a parameter that measures the size of the perturbation, no? In this problem, which are the perturbed parameters? The masses, so M1 is big, okay? But this one, M2, and M3 are small, okay? So this will be my epsilons. Okay, so to speak, that's going to be my epsilon. And then, when epsilon is small, I have a near integrable system. See? Okay? And then what does perturbation theory? Perturbation theory studies precisely this. I have a periodic orbit here. I want to see when I put epsilon positive if the periodic orbit persists. I have a hyperbolic point, and so the talk before was about perturbation theory, no? So here everybody knows about perturbation theory, no? The main idea, or the original idea of perturbation theory, is I'm going to study the solutions of my system that depend on T, but also depend on epsilon, doing a Taylor expansion in epsilon. So I'm going to consider a Taylor expansion with coefficients that are functions on T. This first term is going to be a solution of the integrable system, and then I'm going to study θ1, θ2, if necessary, etc. No? And these are the ideas that people began to use. I'm talking about a long time ago still, eh? So to integrate the three-body problem using this idea. No? So the idea was to write, as in 2 and 3 were small. At those moments, what they tried to do is, well, this is again what they already said, so I can put the next slide. So what they tried to do is to do power series. So they didn't do qualitative theory yet, so just power series. Let's do power series to compute the equations, compute the solutions, so that they didn't have computers, so everything was not by hand. You can imagine, because the equations were quite big. And then there are several results, Carl by Strass, to compute the solution in formal power series. Some people call this series Lister series, okay? And then the question was, okay, you have this power series, are they convergent or no? Because if they are not convergent, okay, if this is not a convergent series, probably what you see in the series is not real here, no? So they don't give you the solution. So there was a big, here you have several things that I found in some places, no? People that was by Strasbourg's convinced that the series were convergent. It says that Dirichlet told Kronecker that he had proven the convergent. So there was a big, let me say, debate about the convergence of the series, and then was when Mittag-Leffler, Mittag-Leffler is this institute that is in Stockholm, was, I think, was a very good friend of Oscar II, the King of Sweden, and then he proposed him to make a competition to the mathematician that was able to integrate, to prove that the series were convergent. And in fact, the competition was called about the stability of the planetary system. And then was when Poincaré appeared. And Poincaré, in fact, let me say, appeared, win the competition, and his proof was wrong. And there is a long story about this that I never know exactly how it was, but I think he won the competition, he got the money. Then I think he made this journal Acta Mathematica or something. And then a student of somebody was trying to read the proof and he found something he didn't understand. And then when he asked him, Poincaré realized that was a mistake. And then he in fact wanted to, say this in English, the prize, give back the money, and it was not possible. There is a long story about this very funny story. But in fact, Poincaré realized the mistake, and then at the end he saw that the mistake is that he was laughing here, you can say. He was trying to find, okay, let me explain this later. The idea of Poincaré, that is where dynamical systems came in, is I'm going to study, instead of studying all the solutions in the field series, which is absolutely possible, I'm going to study some special solutions that give me the portrait of the system. Okay, this was the idea. So, understand the qualitative behavior of the system. Because his idea was, if the system was integrable, what happened in the two-body problem, you would see a very nice and ordered set of orbits. Okay, this was his idea. If the orbits are not ordered and beautiful, etc., this means that the system is not integrable. And then he was, his idea was that, okay, let me see if I can explain this with hex. If you consider this n-1 two-body problem, the solutions are ellipses. Okay? For each two-body problem, you have ellipses. If you consider this in an abstract way, ellipse, this is a torus in this higher dimensional space. Is a torus. So the motion if you consider two-body problems are two-dimensional tori. So the space is foliated by this tori. So if you perturb the system, people was trying to see that this tori persisted. And you know very well that this is what is nowadays called K-M theory, but this came later. Okay, all the answers to that. What Poincaré saw is that in between some of these tori, they appear periodic orbits. Nowadays you know very well the pictures, not that you show the invariant cores and then in the middle the chaos, etc. He was realizing that there were some periodic orbits, and he was able to compute the stable and unstable manifolds of these periodic orbits using power series. Okay? So when you compute the manifolds using power series, what happened is that the stable and unstable manifold coincide at all the orders in the series. So the first conclusion he got is that the system was integrable because the manifolds coincide, and this was his mistake. Because what happens in these manifolds, the intersection is exponentially small in the parameter. Okay? But well, this is a long story. The story is that he finally realized that the manifolds intersect transversally. Okay? And then, if the manifolds intersect transversally, there is all these multiple intersections, etc., the phase portrait becomes horrible, and then this cannot be the phase portrait of an integral system. And this is what I found, this is the text of Poincaré, that says, when one tries to depict the figure formed by these two curves, the stable and unstable manifolds, and their infinite of intersection, each corresponding to a double asymptotic solution, intersections correspond to heteroclinic solutions, no? These intersections form a sort of trellis, web, or infinitely tight mesh. Neither of the two curves can intersect itself, but must fall back on itself in a very complex way in order to intersect all the links of the mesh infinitely many times. One is stuck by the complexity of this figure, and I shall not even attempt to draw. Nothing is better suited to give us an idea of the complexity of the three-body problem and all the problems of dynamics in general where there is no uniform integral and Bowling series theories. These Bowling series are the series I was talking about. So what he realized at the end is that you can find some simple, let me say, solutions to periodic orbits with a stable and unstable manifolds that intersect. And this computation of intersection is a, let me say, Melnikov type computation. And then he realized that if this happens, the system cannot be integrable, and then the series should be divergent. Okay? This is the, let me say, the born of dynamical systems, to study the qualitative behavior of the orbits. Okay? I said here, no, the group was not correct, but the idea is developing the area of dynamical system. The proof of the stability of the solar system is still nowadays an open problem. Okay? There are some partial results, very important. There are some significant results about the possible final motions, and here I'm going to give you some results in the instability dimension. Okay? There are also results of stability, results of KM theory for the planetary system. But I'm going to talk about instability in the last part of it. The ideas that began on Poincaré were developed mostly in the 60s, no? When dynamical systems grew a lot. And in this, Kolmogorov, Arnold, Birkhoff, Moser, Smail, these are all these names that are famous and give us all the tools that we use nowadays. So, now here begins the mathematics. So, the problem I'm going to give you some I'm going to focus is the three-body problem. 3 is enough. You have 3 bodies, these are the equations I showed before. In fact, one thing that is very easy to see, that if you have 3 bodies and the initial velocities and the initial positions are in a plane, then the motion is all the time in a plane. So it has sense to consider the planar 3-body problem. Okay? Because they are going to be all the time in the same plane, so you only need to put 2 coordinates for each. And then this is the reason why Q1, Q2, and Q3 now are in R2 and not in R3 as I said before. Okay? So, but even if they are in R2, 2 plus 2 plus 2 are 6, so 6 second-order differential equations that depend on anything. This is not integrable at all. Okay? So, this is a picture of the 3-body problem. In my picture, Q1 is going to be always the big body, so it's going to be the sun, so to speak. And Q2 and Q3 will have small masses or no, depending on the result. And I want to give you some results about 2 related problems. The final motions that I said before, which is the possible behavior of the solution when time goes to infinity or minus infinity, and the chaotic motions. You will see that the 2 things are very related. Okay. If you are in the three-body problem, even if I said that there was like 12, I don't know how many equations, using all the first integrals, the system is Hamiltonian, reduction, symmetry, etc. Finally, you end with a system of 5 differential equations. Okay, so at the end, our dimension is going to be 5. It's a Hamiltonian system in 3 degrees of freedom, so it is 6-dimensional. But if you fix the energy, you have 5. So the phase space, so to speak, is 5-dimensional. There is another interesting problem that is the restricted three-body problem. Restricted means now I have 3 bodies, okay? 3 bodies. I cannot put these 2 masses equal to 0. I'm going to consider that this mass M3 is very, very small compared with M2 and M1. So I will put M3 equal to 0. Okay? Look at these equations. In the equations there was an mi times this equal to mi mj. I simplify the common mass in the 2 parts. If I put now M3 equal to 0, this is the restricted three-body problem. This is a trick, because if you consider the original equations and put M3 equal to 0, everything disappears. Okay? First I simplify, and now I put M3 equal to 0. This is the restricted three-body problem. If you think the restricted three-body problem, if this problem has no mass, he doesn't influence M2 and doesn't influence M1. So M2 and M1 move freely as a 2-body problem. But M1 and M2 give influence to M3. Okay, this is the restricted three-body problem. In this case, when you consider the restricted three-body problem, M3 0, then the final system is dimension 3. Okay? So it's a big difference in the restricted and the non-restricted. In the restricted you have 3 dimensions, in the non-restricted you have 5. Okay. You know very well what means that a system has chaotic motion. Okay? To study a dynamical system, let me say a flow, what you do always, well, there's no lots of times, is to consider a section and do a Poincaré map. Okay? So for a Poincaré map, if we are in dimension 5, the Poincaré map is going to be dimension 4. If we are in dimension 3, the Poincaré map is going to be in the plane. Okay? So a map in the plane. When you have a map, you say that there is chaotic motion when this happens. So you have a set, which is invariant for your system, for your map, it's an invariant set. In this set you can find an orbit which is dense. This is what is called topologically transitivity. But at the same time in your set you have infinitely many periodic orbits of all the periods. And the periodic orbits are dense. These two conditions together, yeah, they already give an idea of how unpredictable is the system, because when you choose an initial condition, you will never know, if you don't have the exact solution, if you are in a periodic orbit or you are in the dense orbit. Okay? So this gives you that in the future or in the past it's very difficult to know what is going to happen. But whenever you have the third condition, that is the condition that everybody knows in a popular way, that is the butterfly effect, or something like that. No, that if you have, there is a quantity, a number, that depends on the system you consider, no? If it's a macroscopic system or if it is a big system, no? That says that for any epsilon, you can always find two initial conditions that are epsilon close, but that you have time, long time enough, there exists a t, such the solutions now differ more than A. So there is an A that you cannot, let me say, overcome. And this means that this happens in the weather predictions, etc. No? That if you don't know exactly the conditions today, you can don't know what happens if you wait enough time. No? So this is what is called sensitive dependent with initial conditions. So when a system has this property, we say that there is chaos in the system. Okay? So I will talk about chaotic motion. This is the reason of this slide, and I will talk also about final motions. This slide is very technical, but don't look at the slide, just look at me. So in the two-body problem, we said there are three possibilities: bounded motion, parabolic, that means that goes to infinity with zero velocity, or hyperbolic, that means that goes to infinity with positive velocity. XIII, in the 1922, began to think about what are the possible motions if you put three bodies instead of three. And he arrived to the conclusion that you can combine everything. So you can have two bodies going to infinity, the three bodies going to infinity, two that stay together and the other goes to infinity with positive velocity, with zero velocity, lots of combinations. We've done all these combinations. Hyperbolic means that the three go to infinity with positive velocity, parabolic, the three go to infinity with zero velocity, and then bounded means that they are bounded all the time, no? And then they are combinations. Okay, to here this is normal. But then he realized that there is another one, that is this that I wanted to understand. So these oscillatory orbits are orbits that the bodies separate, but they come back. Then separate more, and then come back again. Then separate more, and then come back again. So there is not a lim sub of the distances, okay? But there is a lim if, so they don't go to infinity, because they come back every time. Okay, these are the oscillatory orbits. And then XIII doing, I don't know, I didn't read his paper, so I don't know how he did it, he realized that this was also a possibility. But he couldn't find an example where this existed. He found that this was a possibility, but he couldn't find an example. And this was 1920. What happens in the two-body problem? We know that this is not possible in the two-body problem, because in the two-body problem I said that this was the only possibility. So if you put two two-body problems together, putting the mass is equal to zero, you could have parabolic, elliptic, but you will never have oscillatory. Okay, so this should be an effect of the three bodies together. Okay? Good. So, the questions after XIII is that do oscillatory orbits exist or not? Because it's a possibility that probably never existed. And can also combine a behavior in the past and a behavior in the future. That also in the two-body problem, this doesn't happen. In the two-body problem, if you are parabolic in the past, you are parabolic in the future. So these two questions were done by XIII, and the first example was in 1960. In 1960 there was this nice example of cyclical. That is, you take two bodies in the plane, moving in ellipses, two-body problem moving in ellipses with a small eccentricity. And then you consider the third body in the perpendicular axis. Okay, then this is stable, so it's going to be like that all the time. And he was able to prove that the third body has oscillatory motions. So oscillatory motions is that the body goes up and passes near the origin, goes down, passes near the origin, all the time comes back, and every time goes farther and farther and farther. Okay? He was able to prove oscillatory motion, and also he was able to prove that probably in the past the stays mounted all the time, and at some moment he begins to become oscillatory, etc. This was cyclical. Then Alexeyev in the 70 proved this, that is also true if you consider the third mass positive but small. Okay? What is important for me is this work of Moser, 73, where he gave a different proof of the existence of these motions based on dynamical system ideas and let me say chaotic, the existence of chaos. Okay? And these ideas are the ones that everybody has used here, including me and Jaume in your paper, no? That's going to appear now. So let me pass now to another problem. This is the planar restricted circular three-body problem. So now we have three bodies in a plane, two moving in circles, it's a particular case of Kepler motion, circles, and the third body that has no mass is moving around. Okay? And then for this problem, the planar circular three-body problem, Simon and Gibbert proved in the 80s that is also true that there are these oscillatory motions if you assume that the equation between the two bodies is small. Okay? So M30, and this is very, very small. They proved this. And with Marcel Guardia and Pau Martin in 2016, we proved that this is also true without this assumption of the masses. Okay? This is another result of oscillatory motion. And then here I listed some of the results, quite a lot of results of oscillatory motions. All these results follow the ideas of Moser. Okay? That I will try to explain it on it. Well, this is a slide about this work of Alexeyev and another work of Dynamical that I will skip. And then I'm going to present you the theorem that I have done with Marcel Guardia, Pau Martin, and Jaime Paradela. This is for the three-body problem. Remember, the difference between the restricted and the three-body problem is that in one case we have a system of dimension 3, or a map of dimension 2. In the other case you have a map of dimension 4. Okay? In this case we could prove basically that you can combine all the solutions of the past and the future, including the oscillatory ones, and we only need a condition that all the three masses are not completely equal. Okay? This is the only condition we need. We can combine all the possible motions molecular. We can combine, well, I will explain you in the next slide. The bodies, the three bodies are going to be like that. Now we don't have any condition in the masses, okay? But we are going to take two bodies and going to be all the time close to each other. And the third body is the one that is going to do crazy things. Sometimes going to be bounded, sometimes going to be oscillatory, etc. Okay? This is the theorem. And this is the picture. So this is the question, more or less the theorem, what we prove, more or less is the theorem. Let me spend some time here because I prefer to. So you have the three bodies, Q1, Q2, and Q3. Okay? Our configuration is going to be like that. So I'm going to make after reduction by dimensions, etc. We are in the Poincare dimension 4. Okay? That is so this is my section where I define the Poincare map. Vale. Then what I'm going to do is every time Q3 is going to move and come back. Every time Q3 passes here, I will count how many turns Q1 and Q2 with one around each other. Okay? You understand? So every time Q3 comes back, I count these two have done 12 turns, I put a 12. Then every time comes back again, now 3 turns, I put a 3. And then in this way I compute a sequence. Plus and minus infinity, a sequence in both sides because this is in the past and in the future. Okay? And what I can prove is that, let me simplifying the statement, give me any sequence and I will find some initial conditions for Q1, Q2, and Q3 that realize this sequence. Okay? Can I prove this? Not exactly. Because I need this L that appears here. So I can define any omega k, but I have to add an L. This L is a minimum, a number, so a small number, what means a small number? that Q3 has not gone very far away, because if these two have done only one turn, Q3, because the number of turns is equivalent to compute the time that Q3 needs to come back, you see? If Q3 needs a lot of time, this means that Q2 and Q1 move a lot of time. So if the number of turns has a minimum value, means that Q3 cannot pass very close to Q1 and Q2. So there is a region here that I cannot cross. In particular, they cannot have collisions between Q1 and Q2 and Q3. This means that it's more complicated. No, but basically we prove that there is a Bernoulli shift. So you can take your motion and conjugate it with a Bernoulli shift of sequences of numbers, and the numbers can be not two symbols, but infinitely many symbols, because you can put any natural number in this data, okay, of the thing that. So, in particular, the oscillatory motions will correspond to put a sequence that increases, because this means that the Q3 passes all the time here, doesn't disappear to infinity, but every time it needs more time to come back. So this means that it's going farther and farther and farther. So the oscillatory orbits correspond to take as omega k a sequence that is increasing, for instance. Okay? Good. Well, this is let me say, the statement of the previous thing. There is a set, and you can make a map, that is the Poincaré map, and you can find an invariant set that is homeomorphic conjugated to the Bernoulli shift. Okay? That is the way you prove chaos. This set, moreover, is hyperbolic. So now I have like 5 minutes? Okay. I give you just ideas in the plane, because in the dimension 4 is more complicated. So I said, this is what is in Moser. What I'm going to explain is what is in Moser. What we did here in these other words requires more technical. So think, for instance, in the restricted T-body problem, finally you have a Poincaré map in the plane. Okay, because you consider a Poincaré map and you have a Poincaré map. The oscillatory orbits are orbits that go closer and closer to infinity. So to understand what happens at infinity, what you do, this was done by MAT80, was to do a change of variables that put infinity at 0. Okay? So once you have done this change of variables, you have a Poincaré map, you have a map in the plane, that the 0, 0 is a fixed point. Because infinity, of course, is a fixed point. If you put at infinity, never comes back, no? So after doing this change of variables, by coordinates, you have that the infinity is just a fixed point of your map. And then this fixed point is not hyperbolic. It's a fixed point that if you compute the relation of the map is the identity. So it's not a hyperbolic fixed point. But you can study that in fact is topologically hyperbolic, so it has a stable and unstable manifold. This was done by MAT80 also. Okay? So now you have this restricted T-body problem, you have the map, the infinity becomes a fixed point and has a stable and unstable manifolds. So the proof of Moser was to see, okay, I'm going to consider these manifolds and see if they intersect transversally. Because if they intersect transversally, when you have a saddle with manifold which intersect transversally, you have the horseshoe. If you have the horseshoe, you have chaos, and you have chaos, you have happy. This is the idea, no? First difficulty, that this is not a saddle. As I said, is a point that is not hyperbolic, but you can prove the existence of the manifold. Then here you have a parameter that is the mass M2. 3 is 0, because I am in the restricted case. Then you do perturbation theory. So when the parameter is 0, you can see very easily that you are in a two-body problem, and then these two manifolds coincide. And then you have to do an analysis to prove that when epsilon, the parameter is positive, the manifolds intersect transversely. If you are used to study manifolds, this is done by Melnikov theory. But in this case, it's not so easy. Okay? In the Sitnikov problem, is purely Melnikov theory. In the restricted planar three-body problem, this is more technical, it's more tools, etc. But then let's assume that you have done this. Okay? Once you have done this, you have the lambda lemma. How you prove the horseshoe? You have a saddle, the manifolds intersect transversally, and then as you have a chord that intersects transversally, the manifold, the lambda lemma tells us that this stretches, and then you create horseshoes. Again here, this point is not hyperbolic, so there is no lambda lemma. But then Moser proved himself a lambda lemma for this case. Okay? So this was the proof of Moser, and the proof of Moser was the one that finally, you have this picture, no? That is the one that everybody knows, and then you have the horseshoe, you have the chaotic dynamics, etc. Euler did this for the Sydney-Koff problem. Then, Libre and Simon did the same for the restricted three-body problem. And we did the same, let me say, with other conditions and parameters, what we are only talking about. Okay? This is mainly the idea. So which is the difference when you are in the... and what happens with the oscillatory orbits? I finish very fast. So once you have, that here you have chaos, you have this dense orbit. This dense orbit is an orbit that goes here, comes back, comes back, and never stops because it's periodic, etc. So this dense orbit is the oscillatory orbit because this is the finite part of the space, but this is infinity. Remember that we make a change of variables. So this orbit is going to here, that is the finite part of the space, and approaches and approaches and approaches infinity. Okay, so it's just a consequence of the chaoticity of the motion. Okay? So to finish, let me just tell you that when you are in more dimensions, so in the three-body problem, you have a dimension, a map that is dimension 4. Okay? It is dimension 4 means that the infinity is not a point. The infinity is a disk of fixed points. And that's a disk of fixed points is very bad to study, okay? To study dynamics nearby, because we study dynamics nearby. So here you have the same configuration as before, but this point is now a disk of fixed points. So we have to develop some tools to study this one kind of map, etc., and then to be able to prove also the existence of the system. Finally we succeed, and I think I'm going to stop here because it's...
Thank you, Kenya. Any question or comment?
One comment. Question. Poincaré, the text that is true, price was and he has the money to price. He expends money going mathematical and find all the reason
exactly.
in order to disappear and never.
Exactly. He used the money to make disappear his rock group. Okay, I did it.
Any other comment or question? No? So, please.
There, beautiful talk. Can you give us an idea how the Bernoulli shift is described for this, for instance, for the oscillatory motion?
What do you mean the Bernoulli shift?
How does the Bernoulli shift? How does this appear to describe the chaos? Is it
in this picture? Or
no?
In the
previous, yeah, even in the simplest case that you had before that, which is.
So in the simplest case,
the planar one.
bueno, the thing is let's say. When you have the horseshoe, this is the horseshoe. So,
is it just a horseshoe shift on two symbols?
This is what I was going to do. I wanted to skip this because it's so. Moser does a different thing.
Oh.
Because this picture comes from taking this system that is, let me say, planar plus time. Let me do this simple thing. So, a non-autonomous periodic system in the plane. Then you choose the Poincaré map, the time T map, and then you have a map, and this map has this horseshoe. And for this map, you have two symbols. But imagine that instead of taking the x, y plane, you take t as a variable. Okay, so you have x, y, and t is periodic. And then you do what people in non-smooth system does. You do a section in the space. So choose x equal to constant. And then in this section you have two variables. One is y, and the other is time. And then in these two variables, as time can be seen as a disk, the manifolds. I don't know how to explain it. The picture is like that because it's a little. I never know how to. The picture is like that. You see? Because in one variable you have time, and then the intersection between the stable and stable exactly. So you have the manifold that is the same transversal. No? But if you put time as a variable, this intersection is a circle. okay? Because the point becomes the circle. And then as the manifolds approach, when they stretch, they intersect in the circle one to the other infinitely many times. So when you put these variables time and x instead of x and y, the number of symbols you get is infinite. Because one variable is the revolutions, so to speak. And this is the reason I said before that the chip that we obtain measures this. The chip. Here. So what we do is the shift that we consider, one of the variables is the number of revolutions, that is the time in fact. Okay? So as you have this variable time passes all the naturals. Because in this circle you have infinitely many, every time the manifold spirals and approaches the circle, that is the lambda lemma, written in these variables, you have infinitely many intersections. It's a little complicated to explain, but the main idea of motion is this one. Don't put the Poincaré map, the classical Poincaré map, but consider time or the angle as a variable, and then you get more symbols.
Anyone else? If not, so we thank Tera one more time.
Você já conhece essa chave? Ah, você não sabe onde é? E foi na onda do Luiz, foi? É, o Luiz falou que lá é. Pois é. Tem uns caras que tem que pendurar ele na ponta.
Eu já achei ele, porque eu tô indo lá. Tere, quarta, você vai estar aqui na quarta-feira. Sim.
Quarta-feira
Vai estar na aula. Sim.
Sim.
Aí eu peguei o voo. Daí nós estávamos dentro. Eu cheguei lá, faltaram 10 passos. Ah, porque a casa tivesse certo o nome, ele achava ele. Eu perdi 3 horas. Tomar só um pouco.
Well, let's continue with our workshop. Now we have the first communication of Dr. Mateus from Unicamp, and he's going to talk about on the Hausdorff dimension and Cantor set structure of invariant sliding Unicode sets.
Hello everyone. So this is a joint work with Professor Douglas Novaes and Professor Gabriel Pons, and we will discuss some properties of sliding Unicode sets. So the ambient where Unicode connections live is the Filipov systems, and it's kind of a standard definition. So I will pass quickly these slides, and it's more to fix some notations, right? So we have the Filipov system Z and the switch manifold N. And the Filipov convention is by the differential inclusion. And we have some special regions on the switching manifold. That's the crossing manifold, the escaping, and the sliding. So basically, and in the sliding and escaping regions, we have the definition of the sliding vector field. So basically, a picture trying to model what's happening in this dynamical system is basically you can join the trajectories in the crossing region. You can kind of slide in both the escape and the sliding regions, but you have here some kind of the pointer. It can go. 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 diverging from the region or coming from the region. You can even lose some kind of units that you have in the smooth version of vector field. If you have a point in the escaping and sliding regions where the sliding vector field is 0, you say that it's a pseudo-equilibrium of the Filipov system. And if the point is the sliding region is an unstable hyperbolic flux of the sliding vector field, or if it's in the escaping region and is a stable hyperbolic flux, you say that it's a hyperbolic pseudo-saddle flux. And you have also the complement in the switch manifold of those regions that are the tangent points. And basically, we have we want to distinguish some behaviors, like, for example, this tangent point and this tangent point, we say here that it's an visible fold for the vector field X and invisible fold for the vector field Y, and here the opposite. And if the point is a tangent for X, but it's not tangent for Y, we'll say that it's a regular point. This is to guarantee some kind of transversality and uniqueness of some trajectories. So now you have the definitions to present the sliding Shunikov connection. This is the formal definition, but it's easier to deal with the picture. So basically we have, I will focus in the sliding case, but the escaping case is kind of dual. So we have a point in the boundary of the sliding region, a point Q, where asymptotically in the past it converges to P, and as in the future it reaches P in finite time. And of course P is a pseudo-saddle flux, so it has an hyperbolic behavior. And our main result is that if you have a Filipov system where the vector fields are C11 and possessing a sliding Shunikov connection in the three-dimensional Euclidean space, we can define a first return map. I will define it soon. Associated through the sliding Shunikov connection there. Then there exists a neighborhood U of Q where the invariant set lambda U satisfies these bounds, and the Lebesgue measure is 0, and the closure of the local invariant set is given by this decomposition, where Q is given by this expression, and is a countable set. Furthermore, the properties of the closure of the set are the same of the original set, both the Hausdorff dimension and the one-dimensional Lebesgue measure, and the closure is a counter set. So the introduction here, basically the first return map is given by, notes that if I take a point here in gamma, which is a neighborhood of Q, it can reach by the vector field X, or in this region whereby the action of the sliding vector field it comes again to gamma, or it can come to this gray region and it doesn't come back. So for the pre-image of these points, so if I take the pre-image, I have the first return map well defined. It's basically this idea. Here is the definition of the Hausdorff dimension. It's a standard definition, and some properties. We will use mainly this property 3, 4, and 5. in the proof, and the definition of Cantor sets. So Cantor sets are metric spaces that are compact, totally disconnected, and perfect. The main tool you use to study the first return map is the iterated function systems. So what is an iterated function system, an IFS? Basically, if you have a compact subset satisfying these conditions, it's the closure of its interior, and an index set that's countable. An EFS on K is a family of contractions on K. So it's a family of functions satisfying this condition. And given an IFS and a finite word on the index set, I can make this definition quite directly. And a key concept is the attractor set of an EFS. So I defined a projection in the sequence of the symbols of the index to my compact set, defined in this way. For some conditions, this projection is a singleton, so it's kind of well behaved. This, for example, is a nested sequence of compact sets, so it's not empty. And the attractor set of the IFS is defined by the union of this definition over all sequences, and it's the maximal set satisfying this self-similar property. It's not hard to see that if I apply NFJ in delta, I come again to delta. So an important property of EFS is if I have a finite EFS on K with attractor set delta, satisfying these bound conditions, both below and both a lower bound and a upper bound, and satisfying this kind of separability, the Hausdorff dimension of the attractor set is bounded by S and T, on S and T are the numbers satisfying these identities. But if the IFS is not finite, it's not so easy to deal with the Hausdorff dimension. However, if the IFS satisfies the so-called conformal conditions, you have more control of its properties. So here are the conditions. Again, I will pass quickly over them. And the result for conformal EFS is the Hausdorff dimension of the attractor set of a conformal EFS is the supremum of the sub-EFSs of finite type. Okay? So it's kind of an approximation result. So now we will construct the first return map, and basically here is the idea I give in the previous picture. So basically I have a neighborhood, I induce a neighborhood gamma, then I take the action of X and I obtain a mi R, and I take the saturation by the selected vector field in the past, the saturation SR, converging to P, and I will take these intervals. The pre-image of this interval are the points in gamma R, where the first return map is well defined. So basically, I have this kind of behavior. I have the intervals in mi R, and the intervals in GAM-R. Note that the image of each of these intervals under the action of X and the sliding vector field is kind of an expansion, because this interval, for example, will come to here and then will saturate GAM-R. So it's kind of an expansion, and therefore its inverse will be kind of a contraction. Why kind? Because we don't know yet if the derivative is less than 1. So we'll have basically we take this set of functions. Since the point P is hyperbolic, I can define a map locally and use the Hartmann-Grobman theorem with C1 epsilon linearization, and I will have that in a neighborhood of P, I can make this bound in the first return map. Therefore, each one of those inverses, I can also have this bound, and therefore I will have that it's an IFS. Furthermore, I can find a neighborhood where it's conformal. The invariant set and the attractor set are the same, which makes sense, since the IFS was defined in terms of the P. And we have this kind of decomposition. So I may take a neighborhood satisfying this inequality. It's possible because this is an exponential, has an exponential growth. And then I consider this function, Pu of t, where I take the sum of the derivatives of those functions of the EFS raised to the t power. And notice that since it satisfies this, the value of the function in 1 is less than 1. Therefore, since this function is decreasing, I have that there is a t hat such that satisfies this. Using the results of the approximation by finite EFSs, I can bound my house of dimension in this way. And the bound of 0, of the dimension being greater than 0, is because any EFS with more than 2 functions satisfies that. Consequently, by the properties of the house of dimension, the one-dimensional Lebesgue measure is 0. So now we will study the closure of the invariant local set. Since Q is countable, we will have the same kind of results. And now we are going to prove that it's a counter set. So clearly, the closure is compacted. Given that the house of dimension is less than 1, it's totally disconnected. And we can use the projection to find a sequence converging for any, or a sequence contained in gamma in lambda u that converges to any point in the closure. So since the closure does not add any isolated points, lambda u, the closure of lambda u is a perfect set. So it concludes the main result. And the projection actually is a topological conjugation with a Bernoulli system with infinite symbols, and then we'll have like infinite topological entropy and the other kind of results. We just published this result with Professor Novaes and Professor Pons. This is some references. Thank you for your attention, and happy birthday, Professor Marco.
Well, some questions? Right, let's thank this speaker again. Now, for last but not least important, we are closing our first day with the communication of PhD student named Ias, here from Campus. And he's talking about entropy of ML Bernoulli transformations.
Thank you. Thank you also all the organizers for making this event possible and for the opportunity to be here. Today I'm going to talk about symbolic dynamics, an extended one, and namely ML Bernoulli transformations. And I will talk about some results and entropy about this type of dynamics. My setting will be a probability space, so a sigma algebra measure, and an invariant map, measure preserving on that setting. So let's start with an example. That's the Baker's map, defined on unit square. It preserves the Lebesgue measure, bidimensional. And this map is ergodic, is mixing, have unchaotic behavior, and these properties can be studied by symbolic dynamics. So the name of this map comes from the fact that the process is like the kneading bread baking. So X variable is stretched by a factor of 2, the other one is contracted, and the right half is placed on top of the left half. So when you look to these systems for much time, you notice that this is statistically indistinguishable from the random coin tosses. So it's a deterministic map, but have some random. Well, to coding the Baker's map, you look into the symbols. So to each sequence, to each point, to each orbit, we associate a sequence of zeros and ones. So we partition our space and we look to the iterations of the map. If for some point, some iteration lies in the first half of the partition, then we code by 0. If it's in another one, we code by 1. So this process does not depend much on the points, but how the maps acts on the atoms of the partition. In this example here, we have an orbit given by 0, 0, 1, 1, and so on. And to get the next orbit, we need just to shift the sequence. So we have a space of sequences and a map acting in this space. So we can formalize this by putting a finite alphabet of letters or symbols and considering the sequences being finite of symbols of this alphabet. And we put a metric into the space, and the choice of this metric means that two sequences of symbols are closer if they agree along a central block. So with this metric, this space is compact. It's also a contour set, so it's perfect, totally disconnected. And we define our shift to be just this map that shifts the sequence, and it is a continuous map. Okay, we can put a structure, a measurable structure into the space by considering the sigma algebra generated by the cylinders. Here we have a basic cylinder set that is the set of all sequence of letters that in the input I we have the letter S. And the other one is a more general, so we fix some letters in some indices. These are essentially all the sets in the sigma algebra, in the sense that if we have to prove some property that depends on measure for the map, we need just to prove for these sets. So this applies also for the definition of the measure. We define a probability measure here by choosing a probability distribution on the alphabet. and consider the product measure, and we use that to define the measure on the cylinder sets. Okay, so now we have a probability space. We have a sigma algebra, we have a probability measure. In general, we say that if we have two probability space and two maps, measure preserving, these two maps are isomorphic if we can select two sets of full measure, both invariant, and an invertible measure preserving map that conjugate these two maps. So a Bernoulli shift is just a map that is isomorphic to a shift map. So the Baker map that I showed previously is just a Bernoulli shift on two symbols with distribution equally uniform. So this was for the invertible case. Now we pass to the non-invertible case. Let's start over. So now we have two alphabets and a transition map between these two alphabets. So let's consider the space of all sequence of symbols, of letters. But now in the positive entries we have symbols of A, in negative ones we have symbols of B. The zip shift introduced by Sanaz-Lamé and Medipool is the zip shift is this map that shifts the sequence to the left, but now it's sent to the transition to the image by the transition map in the -1 entry, which now is a symbol of B. So this is the zip shift map. And an extended Bernoulli is just a map isomorphic to the zip shift map. When we fix the cardinalities, we have an ML Bernoulli. So in this setting, we need to define a measure preserving a measure space, which is the zip shift space, and it's just like the other case, but now we have two probability distributions to define our measure. So if you look to the alphabets, when we have two equal alphabets in an identity map, we have a Bernoulli shift. If the B has just one symbol and the A has more than one symbol, we have a one-side shift. I will show you now an example of a map that is not invertible, but is not one-side shift. That's the Baker's 2-to-1. The behavior very similar to the Baker invertible, but now it is stretched by a factor of 4. It's contracting in another direction, and the right hand is placed on top of the left. This is the first iteration, and we show that this is a 2-4 Bernoulli transformation. It's isomorphic to a zip shift with two symbols, A and B, and 4 symbols. And in general, the Baker's N-to-1 is a 2-to-N Bernoulli transformation. Now, we look to entropy. We want to characterize this type of dynamics. So for Bernoulli shifts, they are all characterized by the entropy. Sorry. This problem, the isomorphism problem of Bernoulli shift, dates back to von Neumann, who asked if the shift with two symbols and the shift with three symbols with uniform distribution are isomorphic or not. And this was answered by Komorov, who introduced this invariant and showed that if we have two isomorphic maps, the entropy should be the same. And the definition of this invariant is here, and was inspired by the works of Shannon in information theory. And Shannon defines the entropy of a probability distribution to be this equality right here. And Komorov and Sinai adapt this to define the entropy of a partition and use that to define the entropy of a dynamical system. So years later, Einstein proved that Bernoulli shifts of same entropy are isomorphic. But this is not true for one-side shifts, and not true in non-invertible setting. But it continues to be important to determine if two maps are Bernoulli or not. Well, in the non-invertible setting, we have other entropies defined to look at these maps. One of these is the folding entropy, introduced by Ruel. And the folding entropy is just a conditional entropy. It's the Kolmogorov-Sinai entropy of the partition into points with respect to the pre-image partition, and can be calculated by a disintegration of the measure along these pre-image sets. So working with Varão and Matos, we calculate the Kolmogorov-Sinai entropy of the zip shift and the folding one. So the Kolmogorov-Sinai entropy is just the Shannon entropy of the probability distribution of the alphabet A. That coincides with the Kolmogorov-Sinai entropy of the partition into cylinders at coordinate 0. And the folding is just the difference between the two Shannon entropies of the alphabet A and the alphabet B. So now for the isomorphism problem, it's not true that zip shifts are classified by entropy in general, but if we restrict ourselves to the n-to-1 case and fix the cardinality of the two alphabets, then if they have the same entropy, we have the isomorphism. And to prove that, we use some working ideas. So these are some references for this talk, and thank you very much for your attention.
Some questions? Thank you. Let's thank the speaker again. I'm going to pass to Professor Douglas for our final announcement for the first day.
Okay, I wasn't expecting that. So thank you very much for you all to join us today. So tomorrow we will start at 9 o'clock. Okay, so I see you all tomorrow. An important announcement: the registration form for the dinner is available in the website. So if you pay it and didn't register it yet, so go to the website, you will find the form there. Okay? So thank you all. See you tomorrow.